Now this lesson has a very funky word in it, trichotomy axiom, and that might scare you, and it shouldn't. We'll talk about what the trichotomy axiom is and what it means, and you'll probably feel pretty smart when you're done, because it actually is something that is common sense, that we gave it a name. And let's just jump right into that. Let's say we have, or Isaac wrote a number on a piece of paper. Then he turned the paper over and wrote a number on the other side. There are three possibilities that could happen. The number he wrote on the back could be less than the number he wrote on the front. The number on the back could be the same as the number he wrote on the front, or the number on the back could be greater than the one on the front. It has to happen. One of those three things need to happen. Now this seems obvious. It still means something. Mathematicians recognize that this property of real numbers reveals that real numbers are an ordered set, meaning they have a particular order. And so here's what it means in kind of nerdy language. The trichotomy axiom, and down here tells us where it came from the Greek word tricha, which means in three parts. So what it means is for any two real numbers, remember we talked about Isaac's piece of paper, he had one on the front and one on the back. For any two real numbers, A and B, exactly one of the following is true. Either A is less than B, A and B are the same, or A is greater than B. So there is a particular order to all numbers, and that's why we use a number line, and we'll get into that a little bit later. Now we're going to switch gears and talk about this idea of negated inequalities. A negated inequality means, we see this symbol. I don't know if you can see it very well. You probably can on your paper, but it's basically like crossing out this idea. Crossing out the greater than sign, crossing out the less than sign, crossing out greater than or equal to sign, and crossing out those. Those mean negated. Or also crossing out the equal sign, not equal to. So we would say, well, all of these would be read with the word not. Not greater than, not less than, not greater than or equal to, not less than or equal to, not equal to. Okay? So if we see if x is not greater than 10, then, so for every negated statement, we can so that's like a negative statement, we can replace it with a positive statement, basically. So if x is not greater than 10, that means it must be less than or equal to 10. So for every negative statement, we can switch it with an inequality. Okay? So, like in the book, they also said, how about if you had, let's write it over here, x is not greater than or equal to 6. If x is not greater than or equal to 6, it must be less than 6. Okay, example 1. Draw a number line and graph the solution of x is not greater, or sorry, x is not less than 2. So if x is not less than 2, it's not smaller than 2, it must be 2 or greater. So I'm going to find 2 here, and it must be, here I'm going to write the positive statement, it must be greater than or equal to 2. So that's another trick too. If the negative statement has an or equal to sign, you're going to have the or equal to sign on one or the other. Okay, so in this case it wasn't there, so it's gonna, that or equal to sign will pop up in one or the other. Okay, so x is greater than or equal to 2. That means we do a solid box or solid circle at 2, because 2 is included. And we're talking about x is greater than, everything greater than 2. And there's our graph. So that's fun. Now they give us a graph, and we have to write it as an inequality and a negated inequality that describes this graph. Okay. So what we have here is everything less than 3. So x is less than 3, not equal to 3. Can't be 3. That's why we have an open circle there. So here's one of our statements. X is less than 3. So how do we say that using one of these signs? If it's less than 3, that means it cannot be greater than or equal to 3. And these are equivalent statements, is what we want to say about that. Now we're switching gears completely, and we're going to talk about advanced ratio problems. Not that it should be any harder, just they like to say advanced. Now the trick to doing advanced is just making a little chart of information. The ratio of red marbles to blue marbles is 5 to 7. If there are 156 marbles in the bag, how many marbles are red? So as you notice here, if we said red to blue, like we did last lesson, was 5 to 7, and we want to know how many are red. Do we know how many are blue? No, we only know the total. So what we want to do when we have is do red, we're going to do the ratio. Red, blue, total would be 12. Okay, so here's our ratio. I'm looking to see if they even do actual. Sometimes people do ratio charts and actual. This might help many of you. Okay, so if we do it like this, there are actually 156 total marbles, and we are looking for how many are red. So here we have this information and this information, and we have 3 pieces of 2 fractions. So we've got a whole fraction here and part of a fraction here, and we can just set them up anyway. So ignore that, how we did it before. Let's go ahead and say red to total is 5 to 12. So red to total is 5 to 12. So we don't know how many red, but we know there are 156 total marbles. So this is going to solve it for us. Using this chart will save you a lot of grief if you take your information from a story problem and put it into a nice chart. Very important, okay, because you don't want to get stuck just kind of blindly going into pretending like it was one of those simpler ones. That's why they call them advanced, is there's one more extra step. So then we solve this like we did. We get 12r equals 5 times 156. Okay, divide both sides by 12. And I'm not seeing a really nice way to reduce it, but I'm just going to go ahead in the order, for matter of time, I'm going to give us the answer. When we simplify 56 twelfths, which we could do not too terribly hard, we're going to get, there are 65 red marbles. Okay, now sometimes you might not get what was asked, because I go back, how many are red? You might have gotten blue by accident. Maybe you did this. So we could write in our chart the information we just gained, and then we could, after that, determine if there were 65 red marbles, we can figure out how many blue marbles just by subtracting 156 minus 65 and getting all the information from that ratio. Example 4, the ratio of fish to crabs in the sea cave was 13 to 4. So I'm going to say there are fish and crabs and total. Again, we can use ratio and actual. So ratio, actual, if you can remember what those letters mean. Okay, so fish to crabs was 13 to 4, 17 total. And this is a tricky sentence. If there were 19 fish and crabs, know that that means they're talking about total. Sorry, total. So we would have 119 right there. How many were fish? So again, we're looking for that. So we're going to ignore the C for crabs, and we're going to just use the data we have here. So we could say fish to total is 13 to 17, and we're looking for how many fish, and there were 119 total. And then we're going to go ahead and solve. 17F equals 13 times 119. Divide both sides by 17. Now that does reduce, and again I'm going to cheat just since this is an example, and you don't want to sit and watch me calculate numbers. So you get 91 fish are in the sea cave. Very fun. I actually quite enjoy ratio problems because it's, I mean, this is as hard as it gets. So if you can do this chart and you can set up two fractions and solve a proportion, you'll get these right every time. These will show up on SAT tests, all kinds of standardized tests. So if you can understand this and get it, then it's going to be really good for you in the future. And we're going to use it in geometry too. The team, oh, sorry, this is practice. So you can go ahead and shut it off and then check your answers at the end. Or if you get stuck, go ahead and turn the video back on. All right, the team played 65 games. If the ratio of wins to losses was 3 to 2, how many games did the team win? Okay, so we have, I'll do my chart over here, wins, losses, total. Okay, the ratio. Wins to losses was 3 to 2, so total would be 5. And they played 65 games. How many did they win? So it looks like we're going to do wins to total games. So wins 3 to 5 equals something over 65. So now we do cross product. All right, divide. And 5 goes into 65, let's see, 13 times. So 3 times 13 would be 39 wins. Or 39 times, but we can say 39 wins. All right, letter B, the ratio of hard problems to easy problems. Oh, that's scary. It's 23 to 7. That's not very fair. Hard, easy, total. Hard was 23. Easy 7, 30 total. How many easy problems were there if the total number was 930 and we are looking for easy? So there's our, we've got 7 easy to total. So we have 7 to 30 equals e to 930. And then we solve that. So 30 e equals 7 times 930. Divide by 30, and we get e equals, so let's see, 30 into 930. 30 goes into 900 30 times, so it goes into 930, I'm going to say 31 times. And 31 times 7 would be 217, yes, so I was just checking, so 31. So 7, we're going to get 217 easy problems. That means we have a lot of hard problems. That would never be me. All these will be easy for you because you understand. All right, letter C, draw a number line. I dropped my ruler. I don't know if you heard that. Draw a number line and solve or graph the solution of x is not greater than or equal to 2. Not greater than or equal to 2, so I believe it must be less than. So take that 2, I've got an open circle. Oh, here, and I'll write it. Draw a number line and graph, but what we're going to get then is x is less than 2. So see how we have the or equal to little line? Don't have it when you write the equivalent statement. So x is less than 2 because it's not greater than and it's not equal to 2. So it must be less than 2. All right, here we have this graph. Write an inequality and a negative inequality that describe this graph. All right, so the easier one is to just write the inequality, which would be, it looks like x is greater than or equal to -1. So that one's nice. Then, to negate this, if it's greater than or equal to -1, then it is not less than -1. And those are equivalent statements. And that is it for the lesson.